All right, so welcome to the first of many videos that you will be watching before actual class time. Now, as I just mentioned, you should watch these before class, so hopefully you are watching this before our second class. And so important information, this is kind of like if I was doing a lecture class, the things that you see on the slides are the things that I'd be writing on the board. So generally those are the things that you should be writing down as well. So as I mentioned, it's good for you to take notes, write down with pencil and paper, stuff that happens. And so if you want to know what to write down, basically the things on the slides are the good things to write down. So again, feel free to pause these videos, write down whatever you need to write down, and then you continue on. So the videos will be a bit faster paced than that. So each slide, hit the pause button, write down the important things on the slides, listen to what I have to say about them, then carry on. Also, if you have any questions on any of the material you see here, feel free to write those down as well. And you can either email them to me or bring them up at the beginning of next class. I'll be happy to answer them then. And then last thing about these slides that you'll be seeing here, they have the chapter from the textbook. So where they come from is written down on them. Those are not actually assigned readings, so I don't actually expect you to actually go and read all of chapter 1, for example. They're just there for informational purposes. So if you want to know more information about these topics, feel free to go to that part of the book. And these are for the Beer and Johnson textbook. If you have the Hibbler textbook, there's the last page of the syllabus has the outline of the course, the day-by-day breakdown of what we're talking about and where that is in each textbook. So these are for the Beer and Johnson ones. The Hibbler ones you can relate using the syllabus as well. So first question, since we'll be talking about statics for the rest of the quarter, the next 3 months, good thing to know is what statics actually means. And so this deals with objects at rest. That's why it's called statics, things that are not moving. And generally you have forces acting on these things. So even though forces generally make things move, so force, any sort of push or pull on an object, that sometimes makes it move. In this case, we're assuming that these forces are not making this object move for whatever reason, mainly because they're probably canceling out for some reason. So we'll see that many times in this course. And then the other thing that statics is concerned with is something called a rigid body. And so a rigid body is something that we're assuming cannot deform. So no matter what object you have, if you put a force on it, it's going to deform at least a little bit. If I have a ruler here and I start pushing on it, you can see it actually starts to bend. So that actually deforms. This would not be a rigid body. If I orient it this way, it doesn't bend as much, but it still bends a little bit. Similarly, if I push on this wall behind me, pushing on this wall, I can actually deform the wall. You're not going to see it because it's going to be a very small deformation. And so because these deformations are really, really small in general, we're assuming they're basically negligible. So for statics class, we're assuming absolutely zero deformation. When you get to one of your next classes, CE 220, mechanics of materials, that will deal with actual deformations and you'll calculate how much things deform and things of that nature. But for this class, absolutely zero deformation. I don't care how much of a force I'm pushing on something, nothing happens to it in terms of its deformation. It keeps its same shape. So why is this class important? Well, statics is really the foundation of technical engineering classes. There's a reason why you take this one first. It's kind of like these buildings here. These buildings have a foundation. So statics is kind of like the foundation of your engineering education. Without this basis or this foundation, there's really no other parts of engineering beyond that. There's no buildings, there's no bridges, there's no rockets. And so that's why this is actually a very important class, and it's very important to actually learn this material because, as I mentioned previously, the next class you're going to take, CE 220, Mechanics of Materials. There's also ME 230, I believe it is, which is Dynamics. So both of those classes rely heavily on this material. And then classes later than that rely on material in those classes. And so this is really the first, technical engineering class, the one that almost every other technical engineering class is based off of. So it's very important that you learn this material. So the point of this is to have your buildings look like these beautiful buildings here, not like these buildings that, although maybe beautiful, are not doing what they should be doing. So you don't want your buildings to do that. If you don't like buildings, if you prefer rockets, if you're one of these aerospace type people, you want your rockets to look like this beautiful rocket here, not like that rocket. If you're more into bridges, then again, you want your bridges to be looking like these guys, not like this famous bridge, not too far from here, about an hour south, the Tacoma Narrows Bridge. So if you want to know more information on it, you can Google Tacoma Narrows Bridge and you'll see everything you need to know about it. But this is one of my favorite videos of all time. You can see these concrete, huge amounts, tons, millions, pounds. I don't know how much this thing used to weigh, but you can see it moving up and down here, just incredible amounts. It's got to be 10, 20 feet. This, stream of concrete that used to be a bridge kind of just flowing in the wind like a flag or like a ribbon. Absolutely incredible what air can do to things. I think of air as this kind of very light object that, doesn't really do too much, but the fact that you can do this to a bridge is absolutely amazing. And this isn't even, it's not like this is a hurricane or anything. This is only something like a 40-mile-an-hour wind. So, 40 mile-an-hour is, a decent amount of wind, but it's not, as I said, hurricane force or anything. So I find this absolutely incredible that this can happen. And so obviously you don't want your bridge to be doing this. Although back then, people actually come down and look at this and watch this thing. This thing took probably about a year to build back in 1938, 1939, maybe 1940, something like that. That's roughly when this video was taken. So it took about a year to build this. And I think this video was roughly 8 months after it actually opened. And so in those previous 8 months, people noticed that this bridge would do this and they actually just go down and watch it. That was the entertainment back then, apparently. And then obviously it wasn't built to do that. So obviously it's going to fall down. And so again, less than a year after it opened, fell into Puget Sound. And that was the end of the Tacoma Narrows Bridge. So again, don't want your bridges doing that. So one other thing to mention about that video is ever since that happened, so since that day, anytime you build a bridge now, you actually have to put it into a wind tunnel. So you have to build a scale model of it, put it into a wind tunnel, and make sure it doesn't do that. So lesson learned from that now, every bridge being made now goes into a wind tunnel so that doesn't happen. And so some of these failures that you've seen, the buildings falling over, the rocket, that was a Challenger 1986, or the Tacoma Narrows Bridge. Those failures aren't necessarily things that came from making mistakes in this class, so it's not necessarily statics failures. They're things that are kind of higher level. But as I mentioned, this being statics being the foundational course, all those other things built on statics, and so you can kind of trace it back to here. So they're kind of more things you'll see in senior level classes, the failures that led to those tragedies. So back to sort of basics of statics. Statics is really kind of based on physics. Physics is based on fundamental dimensions. And so you have 3 fundamental dimensions in any system. So usually you have length and time. So length usually measured in either meters or feet, depending on whether they're in the SI or US system. Time always measured in seconds. And then depending on which system you're in, your third fundamental dimension is either mass for the SI system measured in kilograms, or force in the US system measured in pounds. And then all your other quantities, so whether you want to deal with pressure, acceleration, they can all be based off of these three fundamental dimensions. Again, for example, acceleration, length over time squared. So I can take length and time, combine them together to make a new one called acceleration. And as I mentioned, which three you take is based on whether you're using the SI metric system or the US system. In the SI system, metric system, you have fundamental units to go along with your fundamental dimensions. So length in meters, mass in kilograms, and time in seconds. And then again, you can build other quantities, other dimensions, other units based on those. So newtons is a kilogram meter per second squared. So here are my three fundamental units: kilograms for mass, meters for length, and seconds for time. Combine them in a certain way, and I get newtons out of that, which measures force. So I basically made force out of my three other fundamental dimensions. You can make pressure or stress in pascals. So force is really the main one we'll be seeing in this class. Stress or pressure, we see a little bit of that in this class, but that's mainly in mechanics and materials class, CE 220. Acceleration, that's more for dynamics, ME 230. And then generally for SI units, if you want to convert from different systems, you generally just multiplying by factors of 10 and kind of have prefixes. So if you want to multiply by 1,000, you now have kilo. So 1,000 meters is now a kilometer, and so on. So conversions in the SI system are fairly easy, and that's why most people like them. So US system, unfortunately, not easy or intuitive conversion sometimes. The other thing about the US system is that, again, we're not using mass as a fundamental dimension anymore. We're now using weight or force. So fundamental dimensions of length measured in feet, force measured in pounds, and time measured in seconds. And so other important units here, again, because we're generally don't deal with mass, we deal with force instead. It is good to know what mass is, or at least what they're called in terms of units in the US system, and officially mass in the US system are called slugs. And so just like kilograms, if we go back to the previous slide, if I want to get newtons, which is a force, I take my mass in kilograms, multiply it by acceleration, which is meters per second squared. Exact same thing here. If I want to go from mass to force, I take my mass, in this case, which is in slugs, and take those slugs times acceleration, which in this case is feet per second squared. So mass times acceleration gives me force. Slug feet per second squared is a pound. Again, just like kilogram meter per second squared is a newton. So slugs, kilograms, very analogous for the US and SI systems. The other interesting thing about US system is, even though feet are generally what you take in terms of the fundamental unit, so any length is generally measured in feet. For pressure, instead of being pounds per square foot, is usually, at least in this class, pounds per square inch. So you see PSI a lot more than PSF. So again, that's another quirky thing about good old US units, using inches for PSI instead of feet. And then of course your conversions. So 12 inches in a foot, 3 feet in a yard. So in case you don't know those, here's a handy little reference table that you can refer to. Also note that there's different versions of tons. So a metric ton and a US ton are different values. More fun stuff. Going between US and SI units is also sometimes a handy thing to do. Not necessarily in this class, but you have to do it in other classes. So 1 meter is about 3.28 feet. It's about 10% more than a yard. If you want to go the other way, 1 foot is about 30.5 centimeters. For mass, 1 slug is about 14.5 kilograms. In terms of force, 1 Newton is a little less than 1/4 of a pound, or 1 pound is about 4.5 newtons. You can also kind of convert kilograms into pounds. So 1 kilogram is 2.2 pounds roughly, but that's a bit of a dodgy conversion. You really shouldn't be doing that because kilograms are mass and pounds are force, but you kind of get away with it. And then in terms of my class, I generally don't like to mix units, so you'll hardly ever see a question that has both, for instance, meters and feet in the same time, or will not have pounds and meters. I generally don't mix my units, so if there's a question that has meters, pretty much every other unit is going to be an SI unit. If it has pounds or feet, pretty much every other unit in there will also be a US unit. I do that because I want you to use the same system. So if I give you a question in SI units, I expect you to work out the answer and all the steps in SI units. Conversely, if I give you a problem in US units, I expect you to work out the answer and all the steps also in US units. I do not expect you to convert US quantities to SI quantities, then do all the math, then convert back. I do not want you doing that. Part of the reason is that engineering in this country, a lot of it is actually done in US units. So you're going to have to learn to do US unit calculations. And so you might as well start now, not only in your job later, but also in future classes. So the earlier you learn this, the better. And this class is actually not that bad. There's only a few little quirks. If you mentioned a few of them, there's only a few others that we'll see. So this class actually is not that bad for US units. So this is a good kind of introduction. So be sure to use those. Be sure to go through your problems in US units. I know that might be hard for international students, but you chose to work, you chose to study here. You may get a job here. You're going to need to know US units. I'm sorry, it's not my call. If it was my call, everything would be done in SI units, but that's not the way the world works, not the way this country works. So learn US units, unfortunately. So dimension statics is kind of based on physics. It's really based on Newton's 3 laws. So first law of motion, particle at rest, it's going to stay at rest. Again, we're dealing with statics, so I only care about the at rest part of that. So if something is not moving and no force on it, it's going to stay not moving. Or if there's balanced forces on it, it's still going to stay not moving. If there's unbalanced forces, so if there's some net force in some direction, the object is going to accelerate, F equals ma. And then the third law, equal and opposite forces. So again, if I push on something, it pushes back on me with an equal and opposite force. So if I push on a wall, the wall pushes back against me. Again, if I go back to my ruler here, when I pushed it down, it was actually pushing up on my finger at the same time with the same amount of force. So equal and opposite forces, that's, again, those three laws are really what statics is based off of. Newton's law of gravitation is somewhat important. It mainly just converts weight to mass. So again, when we go back to the calculation of converting kilograms to pounds, for example, that's really converting a weight to a mass. And on the surface of the Earth, you have a standard value for the acceleration due to gravity, g, 9.81 meters per second squared, or 32.2 feet per second squared, depending on, again, SI or US units. And so you can relate weight and mass basically just by this equation here, F equals mg, using those values of g. So generally, there's a very simple correlation between the two. If g is always the same value, then it's a simple conversion, and that's why you get away with it. If you start going up into space, then you can't really convert mass to weight. So that's really all we need to know about Newton's law of gravitation. So for us, for statics class, we're generally going to stay on the surface of the Earth. So we're generally going to have these values of G, 9.8 and 32.2 the entire time. You're not going to have to calculate different values at different altitudes. So again, the conversion from weight to mass is very simple. You either multiply by G or divide by G. So if I want to know the weight, I can take the mass, multiply by G. If I want to know the mass, I can take the weight and divide it by G, again, using the appropriate value, whether I'm in SI or US units. So doing this as a couple examples, I have a 1 kilogram body multiplied by 9.81 gives me 9.81 newtons as a force. Similarly, if I have a 200 Newton body, I can divide that by 9.81 and get a mass of 20.4 kilograms. Same thing for the US system. 10 slugs, that's mass. So mass times 32.2 gives me 322 pounds as a force. Similarly, 50 pounds, divide that by 32.2, gets me into a mass of 1.55 slugs in this case. Now, I said the official units for mass are slugs. Many of you probably have heard of pounds mass, which sounds a lot like it should be a mass. And technically, it is a mass, but at the same time, it doesn't work like a normal mass. So like we just saw on the previous slide, if I want to go from a force to a mass, I either multiply or divide by G. So pounds mass is a US unit. And so G in the US units is 32.2. So if you want to go from pounds mass to pounds force, you should multiply by G, right? Wrong. Pounds mass was made to be a very simple correlation. In other words, whatever the object weighs in pounds force is what it has in pounds mass. So if something has a mass, in quotation marks, of 1 pound mass, that corresponds to its weight being 1 pound of force. So if you ever see pounds mass, do not multiply by G to get to pounds force. It's just whatever number is in pounds mass is that number in pounds force. So be careful with these guys. They're a very tricky unit of mass. So that's, again, one of these other quirky things about the US system. I think we got through pretty much all of them that we're going to see in this class. But that is the one thing that is very tricky for a lot of people. You think of a mass, want to get to weight, multiply by G. In this case, do not do that. Essentially, in this case, G is 1, which is kind of weird, but that's how those work out. I obviously don't like pounds mass very much. I'm sure you guys don't either, but the point of what I'm trying to say is that anytime I write pounds, so just LB or just LBS, if I say pounds, if I write down LB as pounds, I'm always talking about a force. The only time I'm ever talking about pounds mass will have a M in it. So LBM is the only time I'm ever talking about pounds mass. Any other LB, LBS, LBF is always pounds force. I usually don't write LBF because pounds by definition is a force. I think writing LBF is completely redundant because pounds is a force. So any pound I write down is pounds force. Only time it's not is LBM. So that's just something for you guys to know. One other thing that students really like to do sometimes is type a bunch of numbers in the calculator, and then whatever the calculator tells them, they write down the entire thing. So if you get an answer of 104.546292.5, students like to write down all those numbers, which you should not be doing. In science and engineering, if you write down all those numbers, what you're telling me is that you know that this is closer to 104.546292.5 than it is to 104.546292.6. So you're telling me you have that amount of certainty in your answer, which you probably do not, because nothing, well, I shouldn't say nothing, but not many things in the world can measure anything to 10 decimal places. That's an incredible amount of precision. In general, you can measure something to 3, maybe 4 decimal places. And so in terms of any number you submit as an answer, it should have roughly 3 significant figures. 3 is a really good number to have. 2 is fine. 4 is not bad. But 10 is, don't do it. So if you get this number on your calculator, instead of writing down all those numbers, answers that I want to see are 105, 3 significant figures, that's perfect. 104.5, that's fine too. That's 4 significant figures. 100, that's either 1 or 2, depending on how you count it, but I'll call it 2, so that's fine too. 100 is better than this entire number, because there's no way you know that these numbers down here at the very end are accurate. So for, again, any answer you put in, unfortunately, the homework won't take points off for it. I wish it would, but I can't make it do that. So if you do type in all 10 numbers, the homework will give you credit for it. However, in labs, on exams, you will not get credit for it. You'll get some credit for it, but you will have points taken off if you write down more than 4 significant figures. So general problem-solving procedure. This is, again, kind of general for any sort of scientific field. Obviously, first steps to read the problem, understand what you're actually trying to find, try to correlate what's actually going on to what you learned in terms of the theory. Understand what the problem is giving you, so what sort of information is given, and then draw any diagrams you may need. So that's kind of important in this class. A lot of problems we're going to see start with drawing something that's called a free body diagram. Again, you probably learned about those in physics class, so same thing here. A lot of problems start with draw a free body diagram with all the forces acting on it. We'll get to those in a few videos. Then once you do that, any equation you might need from the theory, write those down, solve those, get your answer. And you also want to make sure that they're dimensionally correct. So kind of one way to check your answer is to make sure that units work out. So if you're looking for an answer and you know it should be an acceleration, but you end up with units of meters at the end, you know those are not units of acceleration, so something must have went wrong somewhere. So if you carry your units throughout your calculation and do the algebraic manipulation on those units, you should make sure that they work out properly. Otherwise, there's something wrong with your equation. Another nice thing about this class is there's, in a lot of things we're going to look at, there's a lot of ways to actually check your answer. So you can actually make other equations to actually check your answer, so that you can do things many different ways in this class. And so you can actually make up new equations to check your answer. So that is one nice thing about this class, is you can actually use different equations to make sure you get the same answer, to make sure you didn't make any algebraic or arithmetic mistakes. So having said that, even if you don't check your answer using other equations, certain scenarios you can't do that. But even if you do or you don't, doesn't really matter. You're going to get an answer, you're going to get some number. You do want to look at that number and see if it makes sense. You know, if you're looking at something and you get a force on it of 1,000,000 pounds and you're looking at a ruler, you know, does this ruler really have 1,000,000 pounds of force on it? So you don't always know whether your answer is right or not, but you know whether it's reasonable. And so that's always something you should look at as well. You know, does this answer make sense? Is that a reasonable number to get from this calculation? So that's, again, another way to look at your answer and see if it's right or not. And then some big assumptions that we'll make throughout the quarter. So pretty much anything we talk about in this class. First few weeks, we'll deal with particles. So a particle, I'm assuming it has 0 volume, so it's essentially just a point. So any particle is going to have some mass, but it's all localized at a very, very small location. So I don't have to worry about anything in terms of rotation, because for points, I don't care about rotation. All I care about is lateral movement, x direction, y direction, maybe z direction, but I don't worry about rotation. So again, the first few weeks of class, we're going to deal with particles. Then we'll get into the opposite of particles, which are rigid or extended bodies. And speaking of rigid bodies, they don't deform. So again, everything in this class I'm going to assume is a rigid body, so no deformation whatsoever. If it starts off as a straight ruler, no matter how much I push on it, it stays a straight ruler. And then concentrated forces assumed to act at a single point. So again, these are kind of like when I push down on this ruler, I'm pushing down at a single point. It's not my entire fingerprint that's pushing down. It's just one single point on the ruler that's pushing down. So that, again, that's kind of like the particle version again, it's at that single point. So a review of what we dealt with today. So we learned what statics is, study of bodies that are at rest, generally have forces acting on it. Force is any push or pull of one body on another. Statics is based on physics, more specifically Newton's three laws. So first law, anything not moving will stay not moving. Second law, F equals ma. And again, we're dealing with things that are not moving, so acceleration is going to be 0. So essentially what we have is sum of forces equals 0. That's going to be an equation we're going to see a lot in this class. Mass doesn't change from one location to another, but weight could with elevation. Again, we're not going to worry too much about that. Most things we're dealing with in this class will be on the surface of the Earth, where g is a constant, and so there's an easy correlation between mass and weight. Just multiply it or divide by g, unless you're dealing with pounds mass, of course. Speaking of which, should be familiar with both SI and US systems, as well as all the unit conversions that go along with them. And then any algebraic manipulation, you can check that by checking the units or by using more equations that we're going to see later. So that is the first lecture. This one was a little bit longer, went into a few details, a few motivational things, a few things that you probably already know, but still want to make sure that you do know them because they are important for later. So the first few videos will be kind of like that, might go into a bit more detail than you need, just because I want to make sure you have all the details. Then as time goes on, the videos will generally get a little slower or a little shorter. So that is it. I will see you later in class.